So before Frank begins his fourth lecture, I wanted to make a short announcement. It's actually an update on something I mentioned for those of you who were here from the beginning 3.5 weeks ago. It's an update on something I mentioned then about at that time it was a proposed Pan American Advanced Studies Institute for 2 weeks in first week in Santiago, Chile, and the second week in Buenos Aires, Argentina, of the first 2 weeks of January 2012, 1.5 years from now. So actually, since then, NSF approved our application, so this will take place. And you'll be hearing more about it. There's not a big rush since there's 1.5 years, but there'll be some procedure. It won't be as big as this. There'll probably be between, it'll be mainly like this one, well, or like the Clay School, oriented towards graduate students and postdocs with a series of mini courses, and it'll probably be altogether in the order of 50 people, including the graduate students, postdocs, lecturers, etc. And as I say, we'll be actually in 2 different places with some procedure for getting in between them, and there'll be some procedure announced in various mailing lists and things for applying to attend to that, and there'll be support from NSF for some substantial fraction of that number of people, and other people should be able to come getting support from other places. So this is just a kind of advanced notice about that. So now we're ready for Frank's lecture number 4.
In the first 3 lectures, I was talking about a number of models of polymers interacting with themselves and with an interface. And in each of these cases, the interaction was homogeneous in the sense that every spot of the polymer was interacting equally in an equal fashion with every other spot, and the interface where the polymer was interacting, which I spoke about yesterday, was everywhere the same. And what I'm going to do in lectures 4 to 6 is tell you about 3 models in which there is disorder present, so that there is some randomness in the interaction itself. And so things are going to become a little bit more challenging than in the first 3 lectures, but we'll see that even today we will still be able to compute a number of things, and I would say somewhat remarkably. So once you introduce disorder, we will then have to deal with 2 types of randomness instead of 1 type of randomness. There is first a disorder that you choose. Today we will be looking at disorder that lives at an interface, and then you freeze this disorder, and then you will have an interaction that will depend on the outcome of this disorder. And the second type of randomness that there will be then still, as before, is that we will be trying to describe a random path given by a Gibbs measure on a space of allowed paths, but the Hamiltonian in this Gibbs measure is actually a function also of the outcome of this randomness. So we were going to have to deal now with 2 types of randomness, one on top of the other. And in all 3 lectures that are coming up, I'm going to make life easier by only restricting to directed paths. I did that already yesterday, but lots of what I said could have been extended to non-directed paths. But once you go to disorder, it really becomes a good idea to restrict to directed paths, because you can make you can hope still to have some exact calculations. Now, Dima on Monday was talking about what you can do when you have undirected paths, but this is really a rather more challenging problem. So we will be looking at directed paths. I also want to remind you before I get going that in the first lecture I used 2 words, quenched disorder and annealed disorder. And so you can look up the definitions of the quenched Gibbs measure and the annealed Gibbs measure in the notes of the first lecture. And quenched means you freeze the disorder and you try to make statements that are true for any particular typical realization of the disorder. And those are the things that we are mostly interested in. And then there is another version called annealed version, where you say, I am going to average over the disorder in a certain way. These models, annealed models, are typically much easier, but it's very useful to use annealed models to compare with the quenched models. Now, there are people who don't like the terms quenched or annealed. They want to call it something else, but I don't care as long as we know what it is. Okay, so, and you will see this quenched and annealed stuff popping up also in this lecture. So what is it that we're going to do in this lecture? I'm going to look at a version of the problem I was talking about yesterday, but in a situation where the interface is random. And I imagine the following situation. I have my interface as before. You will not need to know what I was talking about yesterday. The talk, I promised that the talks would be independent. I'm going to have some sort of randomness along my interface, and I call these things random charges, but you can think of this being sort of sites that have different chemical affinities with the polymer. So the polymer could be consisting of molecules, and here these things could be sort of hydrophobic and hydrophilic, and so we're going to talk about this disorder in some abstract way, and the goal will again be to determine under what conditions on the law according to which I put the randomness here, does the polymer want to localize or does it not want to localize? And so this disorder will play a role in the interaction that the polymer chain picks up when it hits an interface. Here it hits the interface at a different kind of point than here, and so the energies here will be different, and the question will be, is such a random charge field able to pin the polymer, yes or no? So there will again be, we will again be discussing a phase transition between localized and delocalized. And I will be looking at a version where this disorder is frozen, and I'm also be looking at a version where the disorder is averaged over, so quenched and annealed. And I will be spending quite a bit of time trying to understand when these two models, when you freeze or average over the disorder, really give you different results. And it turns out that for some choices of the law according to which you put this randomness here, it doesn't matter really whether you put the randomness, whether you freeze it or not, and in some cases it doesn't matter. And we use a name for that. We say in one case where it does matter, we call the disorder relevant, or you could call it significant. And in the other case where there is no difference between the two models, frozen or average, we would call the disorder irrelevant, or you could call it insignificant. And what this means that in the case where they are different, then the critical behavior of the two models is very different. And if they're the same, the critical behavior is very similar. So we will be also trying to see how much the answer will actually depend on the realization of the disorder. And then at the end of the talk, I'm going to explain to you that this model can be applied to DNA. In particular, it will, we can apply to what is called the DNA denaturation transition, which corresponds to the strings of DNA sort of separating when you heat the system up. But we will come to that at the very end. Now, the moment you put on this order, you have to realize that immediately something interesting is going to happen, because there will be a competition going on between this path wanting to intersect the interface, but wanting to do that perhaps at good spots where the disorder is such that when it crosses there, it gets a big reward, and not doing it at bad spots, where if it would cross the interface there, it would not get a big reward. So the moment you have this, let's say, random potential along your interface, there is a new phenomenon coming up that the polymer will sort of look ahead and say, okay, I want to cross the interface to get some rewards, but I'm not just going to do this anywhere as I had in the homogeneous model yesterday, where it didn't matter where you would cross the interface. Here it does matter because there are good spots and there are bad spots. And somehow the polymer has to sort of tune itself to this environment and say, I want to intersect the interface, if at all, at the spots where I get a good reward, and I do not want to go to the spots where I would not get a good reward. So there is this spatial competition now that comes up that is a typical feature of models with disorder. So that is something we will have to be able to deal with. Okay, I'm going to set up the model. Now, I usually did this by first giving you a set of allowed paths, then a Hamiltonian, and then there was a Gibbs measure. And yesterday, I also explained, well, I could have started from a random walk, but I could have started more generally. I'm going to turn things around. I'm first going to do things now in a more general language, and then later come back to my path space and Hamiltonian. So just to swap things around for divertimento. So we're going to start with a reference process. It's going to be a Markov chain, a recurrent Markov chain on some countable state space. Could be anything for the moment. And there will be a special point in this state space which are marked by a star. And the law of this Markov chain I will denote by capital P. And I will also always make the Markov chain start at the star point just for convenience. Now, this Markov chain has a return time distribution. So this is an object that we saw in a somewhat different guise yesterday. And this Rn is the probability that this Markov chain, when it starts at this marked point, returns to the marked point exactly after n steps. And in between, it is not allowed to visit the star point. So it's the first return time distribution. So R dot is the return time distribution of our Markov chain S. Okay, I'm going to need some asymptotic behavior of this return time distribution. I will want this to be logarithmically equivalent to a power law. So I want that log, so this will be an assumption, the log of Rn divided by log of n. I want this to converge to minus 1 plus a, where a can be any number between 0 and infinity, including 0. So roughly, so this means that Rn is roughly of this form, but this is really, this does allow logarithmic factors to be added, or even any factors that are not polynomial. Okay. So this is the first ingredient that I want to tell you about, and I need to give you 3 ingredients to define the model. The second ingredient is the disorder, and this is the disorder that is going to do what was in the picture. For me, omega will be an ID sequence of R-valued random variables with some marginal law mu. So there is going to be, so this is the so this is ID, R valued and marginal law mu naught living on R. And I will need to assume something about this law. I want it to have all exponential moments. And there will be a key function. So this is the second assumption, m beta, which will be the expectation of the betath power of a single element. I want this to be finite for all beta in R. So I want the tails of this distribution to be smaller than exponential. Now, I'm also going to assume, and that this will be harmless, I'm going to center the variables and give them variance 1. And on the next slide, you will see that I can do that because I will be putting parameters in front of the mean and the variance. Okay, so this is the second ingredient. And the third thing is that I will now define what the Gibbs measure will be. The Gibbs measure will give, so this is the Gibbs measure that I'm trying to define. It will depend on two parameters, beta and h. And beta has to be non-negative, and h can be any value in R. And it will take a directed path of my Markov chain. So my Markov chain is doing, so S is a Markov chain under this reference law of the Markov chain. And I'm going to tilt this law by an exponential factor. And the exponential factor is you, at all times I running from up 0 to n, if you hit this special marked point in your state space, then you pick up a certain weight factor, which is beta times omega I minus h. And you do that for every return to that point. And then you have to normalize in order to get a probability distribution. So this is the tilting. And the tilting is only seen when you hit this special point. But the amount by which you tilt will depend on a random variable that is given by this disorder. And there are these two parameters. And beta you can think of as the strength of the disorder. And you can think of h as the sort of a bias of the disorder. That's why I decided to make these random variables zero mean and unit variance, because I wanted to play with the parameters here. And that is then the model that we're going to look at. And so this is a Markov chain, in a recurrent Markov chain in a state space that each time it returns to a certain point, it gets reweighted. And it gets reweighted in a way that depends in a disordered way on the time at which it does that. Okay. Now, be careful with, okay, but we'll see that in a second. I'm running ahead of myself. Okay. Now, in the standard, no. The state space in which you can run can be anything. Time is always one-dimensional. So this is 1 plus d-dimensional, where d-dimensional the d would be the dimension of the state space in which the Markov chain lives. Yeah? Okay, so in my traditional writing, this would correspond to picking a set of paths, directed paths, so time is always moving forward, and here is the position of your is a possible location of your Markov chain in your state space gamma. And this is simply the set of all n-step directed paths with no restriction on what they're doing, because this omega I can be anywhere in this state space gamma that you're living. And the Hamiltonian that corresponds to the model that I wrote down is this Hamiltonian here. Each time the path hits this special state star, it has the possibility of picking up some energy, and this energy is going to be random and it's given, apart from these parameters, by this omega I. And the key example that would correspond to the picture that I drew on the first slide is that you would take for your state space the integers. Your Markov chain would be simple random walk in one dimension. And then if I draw a time-space picture of this Markov chain, and I would have to put here, this star would then be 0, then I would exactly be modeling the situation that I've been describing before. And if I would replace this random walk by something more general, I would be allowing steps that are more general. And the simple random walk corresponds to A being equal to a half, except I was a bit sloppy yesterday. Here, this limit here, you may want to take this through, for instance, the even ends. I'm pretending here that it's for every end, but if you're a simple random walk, you can only return after an even number of times. So then you're supposed to assume this thing along the even integers. Nothing really changes much by doing that because you simply restrict life to the even integers. Another example would be where this gamma would be z squared. And then I would be looking at simple random walk in 2 dimensions. It's still a recurrent Markov chain. And so I would then be in a situation where I would be describing a polymer that is moving around in the plane, but time always shifts, and it's trying to interact with a line around which it can wind itself. So there are 2 cases. This could be Z. Star would be 0 in this case, and P would be simple random walk in on Z, and A in this case would be a half. And I can also take Z squared, still make the star the origin. P would be simple random walk on Z squared, and in this case you would get an exponent 0. And there are many other examples that you can cook up that would fit into this picture, but think of the first example as describing the picture that I put on the blackboard before. Okay. Now, by the way, I can put the homogeneous model that I was discussing yesterday into this thing. If I take beta equal to 0, the disorder disappears. And if I replace minus h, if I put h equal to minus zeta, which was the energetic reward that I had yesterday, then this will reduce, of course, to the homogeneous model. Now, what do we expect? Yeah, because the first return time distribution goes like n to the 3/2. It's the first return time distribution of that the Rn is. Okay, so now what do we expect could happen? So this is a sequence that takes both positive and negative values. Maybe I should assume here that it's non-degenerate. And the mean of omega 0 is 1, and the variance is, sorry, this is 0, and that is 1. So that will be, we'll keep that here. And okay. Now, what will we intuitively expect that would happen? If beta is very large, then for the values where omega is positive, this can really get a very low energy, so a high probability under the Gibbs measure. And so for beta large, I would expect that the disorder is able to localize the polymer. It gets a lot of reward when it hits the positive values of omega I. But I don't want H to be too negative then, because then I'm again making this potentially very negative. So for large beta and H not too small, not too large, I would expect localization to happen. So if I start to plot, make a plot here of H versus beta, I would expect that I would localize somewhere out here, because I would be able to target the positive values of omega and get a wonderful reward for doing that, because beta is so large. On the other hand, if beta is very small, the reward for hitting the positive values is not so big. And if H, on the other hand, is very big, then it's going to really make every hit sort of a negative. It will make it a positive energy. So then I won't want to hit the interface. So I should expect that if I'm somewhere up here, that the system will want to delocalize. The disorder is simply not good enough to catch you, whereas here it is good enough. And the H can sort of shift the disorder to negative values, and so that also plays a role. So I should have somewhere here I'm looking for a curve somewhere in between there that would separate the localized phase from the delocalized phase. And the model that we were looking at yesterday, what, as I said, corresponds to beta equal to 0 and H minus zeta. So if we're looking at this line, then here we would see the homogeneous model of yesterday. And now we have something much more interesting, because we have a two-dimensional parameter space. And instead of having a critical point like yesterday, we are now looking for a critical curve. And there is some competition going on between these two parameters, beta and alpha. Okay. Okay, I'm now going to build up the appropriate notions to start to talk about the critical curve that we are looking for. And the way this goes is that I first introduce a free energy, as we've seen before. The free energy, by looking at the behavior of the free energy, you should be able to detect a phase transition. So the free energy is, as always, defined as the exponential growth rate of my partition sum. So this is the partition sum that belongs to the model. And there are the parameters beta and H, but there's also the disorder that is frozen. And I call it quenched because I'm taking a limit at fixed omega. And by standard subadditivity arguments, which work beautifully here because we're in a directed context, and this was explained by Nicolas in the first tutorial, you can prove without much trouble that this free energy exists, omega almost surely, and that it will omega almost surely also be constant. What the value is will definitely depend on the law according to which I choose omega, but it will not depend on the realization of the omega. So this is a standard fact, and Nicolas proved this, in fact, even for this model in tutorial 1. Now, very similarly as in for the homogeneous model, it is not hard to prove that the free energy is always non-negative. Why? Well, the free energy can be bounded below by the probability that my path simply never hits the interface. Because if it doesn't hit the interface, the Hamiltonian is 0 because it doesn't see anything at the interface. So the free energy can be bounded below by the probability that my reference Markov chain never returns to the star state at time t, which is this sum here. And because of this assumption here, this sum is decaying to 0 algebraically, and therefore it's harmless, and the free energy cannot be negative. So there are two options. There can be parameter regions where the free energy is 0, and there can be regions where the free energy is strictly positive. And we're going to give these regions a name, and we will have to identify what these regions look like. They would be corresponding to the two regions that I have sort of indicated there. And we want to call this one 0 because if I have a delocalized strategy like I was getting for this lower bound, if I say if you never hit the interface at all, well, then you are building a free energy that is 0. So if you have a delocalized strategy, then that will correspond to a free energy 0. And apparently, if you are able to cross the interface a lot, you might be able to raise your free energy by doing something that is better. So there is still this picture here that we're trying to go after. There will be a localized regime where we expect the polymer to sort of hit the interface a lot, and there should be a delocalized strategy where it maybe hits it a few times and then simply wanders away either on the positive or on the negative side. So that's the thing that we're trying to capture. And we can define, so these are the two regions. For the moment, I don't know where they are. All I know is that the D region should contain the upper left part, and the L region should contain the right lower part. But we will have to see what is happening. Now, here is a first result that was proved in a very important paper by Ken Alexander and Vladias Sidorovicius. You can define the quenched critical curve as the smallest value of h for which you are still in the delocalized regime. Well, here an important remark is necessary. Because the parameters beta and h appear linearly in the Hamiltonian, the free energy is a convex function of beta and h. When beta is equal to 0, it is, and h is equal to 0, it's 0. So it's a convex function that actually, because it has a sign, it's a non-negative function. It also has certain monotonicity properties. And this function is, as you immediately see from the Gibbs measure, it is an increasing function in h. So this is well defined. So there is some curve that I can define here, and that would be just a curve that is just at the boundary between these two regimes. So this curve is trying to, for every beta, tell you where the boundary is between these two regimes. And it was proven in the paper by Ken and Vladas that this critical curve is positive for every beta, so that it actually looks something like this. Well, at 0, there is no interaction, and we go back to the critical value that we had for the homogeneous spinning, because there the critical value was 0, and it will be some sort of curve that looks like that. And again, from general principles, you can easily check that this curve is a convex function because it's a level set of a convex function, namely the free energy. And level sets of convex functions are convex themselves. So we expect this curve to typically be sort of looking like this. So this would be the H critical quenched as a function of beta. Okay, and what was an interesting fact is that they proved that this curve is, for every positive beta, above the axis. Now, why is that an interesting result already in itself? Well, the mean of my disorder is the mean of, the mean of my energy that I pick up at a certain site is, so the mean value of the disorder, so this is the mean value of the disorder, the energy at a site, any site. Well, that is, the average of this is 0, is minus h. So as soon as I make h positive, the average disorder is going to be negative. So on the average, the interface doesn't like you to intersect. On the average, it gives you a penalty for intersecting. Yet, it is the case that if I make h small enough, that I can localize. So what the fact that this curve is positive is telling us that if h is small enough, then even though on average the disorder is repelling you, you can still localize. And why is that? Because there will occasionally be a few points of the disorder that are positive, because the disorder has mean 0, so it will have both positive and 0 and negative values. And so only a few points where it is positive, even though the rest could be negative, can be enough to pin you. And how do you do that? You look at your disorder and you say, I see many, many negative values. You know what? I'm going to just avoid them. And I see a few positive values. I say, I will go and find these values, and I will get my reward by visiting these few positive values. The fact that that works is the message of the fact that this curve is becoming positive immediately. And that was an issue for a while, and it was settled. And in a way, this paper was the start of a whole bunch of papers that appeared later on the model. And some, I will mention some names coming up later. Okay, now I do want to make some more progress on what this curve looks like, because apart from the fact that it looks like this qualitatively, we have, for the moment, no details about what this curve exactly is. This is a complicated curve that is not easy to compute. Now, I'm going to look at an annealed version of the problem, in which I'm going to average over the environment in a certain way. And the annealed free energy is defined by first taking the expectation over the disorder of your partition sum, and then seeing how that average grows. And this is very different from putting the expectation before the logarithm. If I would do that, I would recover the quenched free energy, because the growth rate of the thing without the expectation is almost surely constant. But the fact that I put it here makes this thing bigger. And this is another free energy in another model. And this model is actually just some homopolymer model of the type I was describing yesterday. And this again has all the convexity properties as the quenched free energy had. I can also define an associated critical curve for the annealed model. But this is just a critical curve of some shifted homopolymer model, and it is a very trivial calculation, which I'm not going to do, to show that this critical curve is actually just given by the logarithm of that moment generating function. So this is another object, not a hard object at all, but we're going to use this object to compare to the quenched model. So we are really after the quenched model. And so here is a general fact. By Jensen, when you pull the expectation under the logarithm, you can only go up. And so the annealed free energy is always an upper bound for the quenched free energy. And because of the definition of the critical curves, it means that the annealed critical curve is always an upper bound for the quenched critical curve. So this brings us to the situation that if we try to get our hands on this object here, then so let me draw something here. There is here a very simple curve, which is the annealed critical curve. And then I know that the quenched critical curve that I'm really after should somehow lie below it. And it may, a priori, it could touch it a couple of times, but we will be seeing that there will be a unique value of beta critical where these terms start, where these critical curves start to separate. So for small enough beta, there will be no difference between the annealed and the critical, and the annealed and the quenched critical curves, and therefore we have complete information about what the curves are there, because this annealed critical curve is so simple. This is not the object that we are after at all, but it is useful for a comparison. And then there will be, when you are beyond that critical value, then the two curves start to separate, and that is the picture that we will try to pin down. And so this notion leads us to a definition which I have already mentioned briefly at the beginning. So if you can fix your return time distribution of your Markov chain, and you can fix the law of your disorder, and then you can say you say the disorder is called relevant if the quenched critical, well, you also fix beta. Then you say the disorder for that choice of parameter is relevant when the two curves differ, and it's irrelevant if they are the same. So somehow, if they are the same, then apparently the fact that I took the expectation over the disorder didn't really matter much for the critical curve, or didn't matter at all. And so somehow it is saying that, and I'm being a bit qualitative here, the statement that I'm about to say should be made much more precise, is that somehow the disorder doesn't affect the qualitative behavior. Okay, so, and this picture already indicates that apparently the change from irrelevant to relevant disorder is happening at a critical value of beta. I will write down a theorem stating that precisely. So somehow if the disorder is very strong, then it really makes a big difference if you freeze it or do not freeze it. And if the disorder is weak, then it does not make a difference. But we will have to worry about whether this value is actually non-trivial. You could say, well, maybe this value is at infinity, in which case the two curves would always coincide. Maybe the value is at 0, in which case the curves would always be different. And sometimes it can be in between. Well, these are cases that we will have to clarify. Okay? So what has happened in the past couple of years around this particular question of identifying this behavior in the phase diagram that I wrote down. Well, there have been a whole bunch of papers, and I've written names of people who were authoring these papers, trying to get your hands on this phase diagram and also identifying for what choices of R, in this case, what values of A, what types of disorder, and what choices of beta do I indeed have these two different kinds of behavior. And it has been fairly well understood what the classification of this distinction between relevant and irrelevant disorder is. So classifying when the disorder is really felt or whether it's not felt in the disorder behavior. And what I want to talk about here is a new approach in which we are going to derive variational formulas for both of these critical curves. So we're going to really write down expressions for them. And then we're going to compare these variational formulas and try to pull out whether or not these curves are different by studying these variational formulas. Okay, so that is the thing that I'm going to do. And to do that, I'm going to need a large deviation principle that I proved in a paper with Matthias Birkner and Andreas Greve 2 years ago. And this is actually, so what I'm going to do is to tell you first a little bit about this large deviation principle, and then argue why it is relevant for this particular polymer model with pinning. And this large deviation principle is a difficult but also very versatile tool. So far we have actually applied it to already 6 different models, of which the random pinning model is one. And so what I'm going to do in the next slides is difficult, but I'm nevertheless going to try and convey to you the main message. And there will then be a point where I say, okay, from this point on we can go on even if you haven't understood all the fine details of what I'm going to say, because then we'll have variational formulas and we can look at them, and there are only a few key things that you would need to know. Okay, I'm going to, so what I'm going to do next is to talk about 5 things that I have to explain to you before I can put these variational formulas on the blackboard. And to make things worse, I'm even going to go through the next 5 slides in a different order than in which they appear here, because, you know, one always learns. Okay, so for this we need to change our perspective a little bit. I want you to think of the disorder as a random sequence of letters that I draw from an alphabet. Okay, so let me so the disorder becomes a letter sequence. Becomes an infinite sequence of letters. Okay, and I can define the set of all probability measures on infinite letter sequence that are shift invariant. So I will call that so the alphabet is R, and P invariant of R to the power n naught is going to be the set of shift invariant probability measures on letter sequences. And a typical element of this we would denote by a large psi. So psi will be a typical element in the set of shift invariant probability distributions. Now, our law on omega is an element of that sequence because omega was drawn in an ID fashion. It was mu 0 to the power n. And so our law is definitely in this big space of all shift invariant probability measures. Then what I need is the second ingredient is I want to look at strings of letters, and I would call them words. Strings of an arbitrary length. So I will introduce an object which I write like this, and this is the set of finite words. I can cut a piece of my letter sequence out, and this would be a set of words. And I can define, similarly, the set of shift invariant probability measures on infinite sentences. So if I draw words according to some sequence and I read them as a sentence, then I can imagine that there is a law of this, and a typical element of this I will denote by Q. Now, if I look at how my Markov chain is doing renewals on my disorder, then I can think of the return times of my Markov chain as loops. I can plot my disorder here and thinking of them as a sequence of letters. And therefore, I can imagine that the returns of my Markov chain are actually, what they're doing is that they are reading off words from my infinite letter sequence, which is the disorder. So I make a return. I look back, I say, I have just seen a word of 12 letters, and it looks like this. 12 words. Okay, then I make my next renewal, and I say, oh, I've just seen a word of length 23, and its content was given by the disorder. So what my Markov chain on top of my disorder is doing is basically cutting out words from my disorder sequence, and the words have a random length and they have a random content. So the typical sequence of this words as my Markov chain is doing it is just running a renewal process on these words, and therefore the way the sequence of words that I will see here, which I call an infinite sentences, will also be a product measure if I do not freeze my disorder, and it will be again an element of the sequence of the set of shift invariant probability measures on words. Okay, so somehow this words cut out from a random letter sequence according to a renewal process is something that should have something to do with our random binning model. And it does. Okay, now I'm going to go 2 slides ahead. Sorry for changing the order, but what we have proved, and this is the key thing, is that we have proved that if you look at this sequence of words that my Markov chain is cutting out from my letter sequence, which is my disorder, is that the probability that this sequence satisfies a certain large deviation principle. So we are not only able to say what the typical sequence of words is that you get in this way. Well, that's just what the typical renewal does on the typical disorder. But we're even able to tell you with what probability you are going to see something very unusual. For instance, I might make a very big jump to a certain particular part of the disorder, make a couple of very short runs there, and actually see a sequence of words that is very atypical, and I can tell that this large deviation principle will tell you with precisely how likely or how unlikely that is. And in the tutorial this afternoon, Francesco is going to give you some background on this LDP, and he's in fact even going to give as a startup, a kind of little crash course on Sanoff's theorem in large deviation. And then he will explain some more background on how you should read the large deviation principle, still in the language that I'm talking about here, and will explain to you why it is so deeply linked with the random pinning model. But you should by now have clearly a feeling that this is going to be able to describe this. So to cut a longer story short, during this lecture, we prove a large deviation principle, both quenched and annealed, for how likely or unlikely it is that you will see a certain infinite sentence when you sample it with your Markov chain on this frozen disorder. And the annealed one is a very easy one, because this is basically, once you average over the disorder, it's a statement about an ID sequence of words. When you land somewhere, and if the disorder in front of you, if you average over, is independent, so each time you land, you start afresh, and that's easy. But the large deviation principle for the frozen disorder is very subtle. And why is it subtle? I stand here, my disorder is frozen. I step 12. I see a word of length 12. I now step 23. I see a word of 23. But what I see in my word of 23 will depend on whether my previous word was 12 or 13. Because if the previous word had length 13, I am seeing a word of 23 shifted. So when I froze the disorder, these words become very dependent. For one reason, if I take the words back again, I concatenate them, and I look what letter sequence I get, it must be the one that is the frozen disorder. So there are big constraints going on. And to get the large deviation principle for the frozen case is really difficult. And the fact that it's difficult is important, because it allows us to describe something really deep, which is this curve here, over there. It doesn't, yes. So again, for almost surely all realizations, it doesn't depend on the disorder, but it's not equal to the quench rate function. So now I'm going to throw something very tough at you, and again, I don't expect you to grasp all the details here, but I want to convey, to show you some structure of this, and then for what we will do later, we do not need to really recall all this detail, except for one particular simple point, which I will point out. So there are quench and annealed rate functions. They are given in terms of what are called specific relative entropies. So relative entropy is a kind of notion of distance between probability measures. In the space of probability measures, you can quantify how different two probability distributions are from each other by looking at what is called the relative entropy. And it's a kind of pseudo distance. And the specific relative entropy is basically the relative entropy per site if you look at probability measures over very large blocks. A key notion in ergodic theory. And then there is a law of my disorder, which appears here. It's just the disorder law to the power n0, and this is an element of my shift invariant probability measures in states on my letter sequences. I also can put the renewals and the disorder together, and I will generate by that an infinite sentence, and the law of my infinite sentence will be also some product measure if you average over the environment. And then if I am given any probability distribution on a sequence of words, I can concatenate the words and say, after I've concatenated them, what letter sequence does that give me? So with every law on infinite sequence of words, there is a projected law living on the probability measures of the letters that I would denote by psi of q. So this is a kind of projection when you say, I don't look at the renewals, I just look at the letters that I get once I've concatenated the words. That's because the word, I count the first word by 1 and the first letter sentence by 0. So that there's no reason for that. It's just because I wanted to fit it into the thing. So this is a complicated thing, but I want you to remember only one important thing, and that will be really the clue to what will explain this term, is that the quenched rate function is the annealed rate function plus an extra term. That depends on the law of the disorder and the law of my Markov chain. Yes, it's always greater than or equal to 0 because there is a standard inequality saying that quenched rate functions are always at least as big as annealed rate functions. That is because if you freeze the environment cannot help you anymore. And so probabilities to realize something only on the basis of the renewals is going to be harder than if you your disorder is allowed to participate. So averaging over the disorder will make the probabilities of deviations smaller. A is this exponent. Thank you for reminding me of that. So this exponent here is entering in this difference term. Okay. Now, these formulas are complicated, but all that I want you to remember is that there is a quenched rate function, there is an annealed rate function, and they differ by something that is explicit. Now, the fact that this difference is explicit is already something special, because very often in disordered systems you say, well, there is an annealed rate function, there's a quenched rate function, but it's very difficult to relate them. And here, apparently, the difference between the two is something explicit. It involves the tail of my return probability, and it involves something that has to do with projecting measures by concatenating words. So, and there's a specific relative entropy, but it is there, and it's explicit. So this is the last difficult slide, and then I will be able to write down the variational formulas for the critical curves that I'm after, and then we can start to discuss those and sort of forget the more complicated theory that is behind it. In order to define that, I'm going to say pick any probability measure that is living on sequence of words, so infinite sentences, so the type of things that we know all the large deviations of. And you can always, if you have this whole sequence of words, take the first word, and of that word take the first letter. So you project onto the first word, onto the first letter, and you get a law that lives on the real line. And I want to introduce a function that says if you give me an infinite sequence of words, then please tell me what the average value is of the first letter in the first word. So that will be phi of q. So it's an integral over the real numbers of this projected law. And let curly C be the set of all shift invariant laws on infinite sentences such that the absolute value of that first letter of the first word is integrable. Okay, so there is a certain very simple function that only looks at the first letter of the first word, and there's a set of measures for which this thing is finite. And now I'm able to write down the first theorem. And the first theorem says there are variational expressions for the critical curves that we're interested in. The quenched critical curve is the supremum over this particular set of all laws for which the first letter has a finite absolute mean of beta times this mean minus the quenched rate function. And the annealed critical curve is the same, except that the quenched rate function is replaced by the annealed rate function. And the way this comes about is that you say, if I pick a particular possible law in which my renewals can generate infinite sequences of words, then that will cost me this much on an exponential level. But each time I hit the interface, I get a reward, and the reward is beta times the value of the first letter minus h. Now the minus h that was in the reward goes to the left, and then you say then the critical value should be determined by the best thinkable way in which I could move through my environment and then say how much do I have to pay for that. That's what my quenched rate function says. And how much do I gain? That is this beta phi q, because phi q is just the average value of the first letter of the first word. And each time I land, I just see the first letter of the first word. So there is a structure here. And if I do the annealed model, I have the same formula with the annealed rate function. And the beta dependence is very simple. It sits in front of here. None of these other quantities depend on beta, but this one definitely depends on the R distribution, and it depends on the mu zero. These are all hidden in these two rate functions. Now, I'm skipping over many technical. It was the specific relative entropy of Q with respect to the reference, the typical Q that you get if you let your Markov chain cut out words. So it's a specific relative entropy. Okay. I do not need this variational formula to tell me what this is, because I know already that this is the logarithm of n beta. But it is here because I want to use it to compare with the formula here, because this is the object that we don't know what it is. This is the real curve that is hard to describe. And now, the fact that this quenched and annealed rate function differ by something explicit. It wasn't an easy thing, but it was very explicit, should allow me to compare these two variational formulas. Because this is just a bit bigger than that. Since it's non-negative, it fits with the size that the quench critical curve should be below the annealed critical curve. But if the extra thing is sort of significant enough, I should be able to separate these variational formulas. And if it's not significant enough, I should not be able to separate it. So, trying to tell you when these two values are the same or are different amounts to be able to say something of the type, let's find the maximizer of this variational formula, which fortunately we can do because there is a very nice simple structure in the annealed rate function. It belongs again to the story that annealed models are always easy to deal with and you compute. This thing has a very simple unique maximizer. So that is, when I substitute that maximizer, I get the highest value. And then I want to show that at that maximizer, if I substitute it in here, this extra term is really positive, and therefore it drives down the critical value from the annealed value, or perhaps in some other cases it's not able to do that. Okay, now this maximizer of this annealed variational problem has a very simple form. It's again a product measure. It's the product measure that you get by saying put a little bias on your disorder. Each time you hit a letter after renewal, so you start a new word, then tilt this first letter by an exponential distribution, exactly given such that this exponential moment here is normalizing. So it is the law that you get by running your Markov chain. It reads off infinite sequence of words, and then you say, at the points where you hit with the typical Markov chain, just tilt your disorder with an exponential factor. You then get a disorder that is sort of tilted at random points. The random points are given by your renewals, and that is a new law of your disorder. And you have to make things shift invariant, so that, but let me not go into those details. So the message is, the annealed variational formula has a very simple maximizer at some product measure, something completely explicit. So that puts it into good business, because the second theorem says there will be a separation between the annealed and the quenched critical curve if and only if the two rate functions are different at that particular maximizer. Because this maximizer realizes the annealed value, and if this extra term here at that particular maximizer, which has a very simple product structure, is really different from 0, then there will be a gap. And if it's not, then there will not be a gap. So here is a complete classification of, in terms of these rate functions and a very explicit maximizer, which is a product measure, to tell you when you have disorder relevance. And the law of your disorder with which you started and the law of the renewals with which you started are all hidden in these two things. They are also hidden in the extra term. So whether or not this is true is going to depend on whether these two things are happening or not. But it puts us into business. And it's an if and only if criterion. Okay. So this comes out of these two variational formulas and comparing them, and you need some arguments of existence of maximizers and continuity properties, but it's basically, well, that can be done. The third theorem says out of this nice classification comes indeed the observation that there is a unique critical point at which this separation will, such that above this critical point there is this separation, and below the critical point there is not this separation. And the fact that there is a unique critical point comes out of certain convexity properties of relative entropy. So the fact that this difference term has a structure that says it's some specific relative entropy of what I get by concatenating words, projecting down on letter sequence and seeing how much I differ from my typical letter sequence, that relative entropy has convexity properties, and that convexity properties is what allows you to conclude that these two curves can only start to separate at a unique point, and they cannot sort of return and to hit each other any further. There.
So the difference between the two was given by your age of
Yeah.
side cube.
Yeah.
And so do you know when this vanishes or not?
Yes, I will give you criteria for that in a second. But this theorem says, as a function of beta, it goes from not to yes, and then that's it. It cannot change more than once. Okay. So indeed, we have the uniqueness of the critical temperature as I wrote it down. Now, what we're going to do in the last 10 minutes or so, I am going to now focus on this value here and say we now know that the picture looks like this. There is some critical value. But you could say, well, could this critical value be 0? Could it be infinity? Or could it be somewhere between 0 and infinity? And we will see that all three cases are possible, depending on the choice of R and mu that I make. So I want to formulate three corollaries that are coming out of this. Now, these corollaries are also results that have been obtained in the papers that I cited, who didn't do the large deviation or variational approach. They were sort of estimating the free energies and estimating the critical curves. And so there are other ways to get this same result, but we are currently in the process of trying to sort of even sharpen the things that we know now and then really nail down the complete picture, because we have this variational representation. And because we have this if and only if criterion on when the curves are going to separate or not. So let me flash 4 corollaries at you. The first, and I'm going to speed up a bit now because I want to talk about DNA also at the end. There's a quantity here that is chi. It's the sum of the square of the probabilities that the Markov chain returns to the state star at time n. And think of this as the average time that 2 independent Markov chains would meet at the state star. And then there is a theorem that says if the exponent a here is 0, so this would correspond to my polymer doing in the vertical direction a 2-dimensional simple random walk, then the beta critical is infinity, no matter what law of disorder that you put. So in the case where I'm having a 2-dimensional simple random walk sort of trying to interact with disorder on a line, these curves are just going to be the same everywhere, and the disorder, no matter how strong you make it, isn't able to do anything. It's not able to capture to localize the simple random walk. If the parameter A is not 0 but is strictly positive, then the prediction is that the critical temperature will be 0 if this number is infinite, and will be positive, possibly infinite, if this number is finite. So this part has been proven. This part is, we're trying to working on that. We can do part of the case, but we want to really nail it down entirely. So in the literature also this part has been proved up to certain cases that cannot be treated yet. So basically it says if two independent Markov chains meet infinitely often at this special state on average, then the disorder is always relevant because the two curves start to separate immediately at the critical value. So then there are some more results. You can get bounds on the critical curve. Let me flash two formulas at you. So here's the critical value, and there you can get lower and upper bounds. And the lower and upper bounds are given in terms of whether certain inequalities are true, and on one side of the inequality is something that only depends on the disorder law, and on the other side of the inequality is something that only depends on the law of your Markov chain. So this thing depended on the law of your Markov chain, and here is the moment generating function of the law of your disorder. So if there is some inequality going on, you can try and find a lower bound here. And similarly, if you are able to compare the entropy of your disorder of your first time law with the relative entropy of your tilted law with respect to original law, you can get an upper bound. So these are technical things that come out of the calculation and that allow you to get some control on bounding this thing. And these numbers can still be 0 or can still be infinity. Sometimes they are, sometimes they're not. Last thing I want to show is that you can also, here's a criterion that allows you to rule out beta critical being infinite. So if you have a disorder law that doesn't put any mass on the top, so the largest value doesn't receive any mass, then the critical value cannot be infinity. So there are some things that are popping out of this variational description, and one can even get more detailed results. If I'm willing to assume something a bit stronger on the return time distribution rather than this logarithmic stuff, but I really want it to be a power law times something that is slowly varying, then I can exactly tell you when this chi is finite or not. And it's finite if my exponent is between 0 and a half, or if the exponent is a half and there's something about the slowly varying function, and it will be infinite exactly when this is failing. And the simple random walk is in the case where chi is equal to infinity. And so it's just on the border between these two cases. So the one-dimensional simple random walk is something where one would say it is very marginal. I mean, the disorder can in fact, you can in fact see a finite beta, but it's marginal. So, and this is a very difficult case. It turns out that, in fact, we still do not have the answer for the simple random walk. So the one-dimensional simple random walk is even the most difficult case. Now, so message is out of this variational formula pops out nice estimates about this critical value. And the fact that a half is a critical value is something that can be traced back to a principle that was formulated 35 years ago. It's called the Harris criterion. It's a criterion that lives in the world of physics of disordered systems. And the statement is of the type, if you have a homogeneous model, and this homogeneous model has somewhere a phase transition that is of order less than 2, so it means that the way the free energy sort of changes there is not quadratic but a bit more dramatic, then if you switch on this order, even a tiny little bit, you will qualitatively change the behavior of the phase transition. And if this is not happening, then you will not qualitatively change it. And in the tutorial yesterday, Francesco showed that for the homopolymer, the order is exactly smaller than 2 when A is a half, and it becomes 2 at a half and higher. So indeed, the fact that this A half is a critical value for changing of the disorder is already in this Harris criterion. The Harris paper is very interesting. It contains a lot of very deep ideas. It's hard to read if you do not have a physics background, but it's still today worthwhile to read because of the many deep ideas in there. In the remaining 5 minutes, I'm going to tell you about how this applies to DNA. So DNA, as we know, is a string of 2 base pairs, AT and CG, and they sit in a double helix, and they occur in some sort of erratic order. And the A and T are bounded by 2 hydrogen bonds, and the C and G, they share 3 hydrogen bonds. So the strength of the interaction between these two is very different. Now, I can view these 2 strands with a bit of imagination as one strand sort of moving around in space, having the other strand as a kind of hard wall on which it might or might not attach. And let me draw a picture of that. So if you heat up DNA, it could be that temporarily these bonds break and you have these sort of, I would call them denaturated loops. And the way of schematically looking at DNA in this way is called the Poland-Chiraga model. And you then can think of this thing as sort of making excursions on top of a wall. And when it hits the wall, it would mean it binds. And the binding can take 2 different values because the strength of the base pairs, in the couplings in the base pairs are different. So you can think of DNA in this picture as the model that we've been talking about with binary disorder. And there are 2 phases. The localized phase would correspond to the phase where the 2 strings of the DNA are really bound together as they should be. And the delocalized phase would correspond to the fact that this disorder is not strong enough, this binding is not strong enough, and the strings would sort of denaturate. So if you take DNA and you start to heat it up, you will see that the strings are going to separate. This is called denaturation. And so this kind of denaturation with a lot of leap of faith is something that this spinning model is describing in some sort of way. Of course, what's happening really inside a DNA molecule is so much more complicated than the simple model that we have talked about, but I said already yesterday what Yuval Perez said. Reality is there to inspire good theories. So somehow the denaturation transition happens when you heat up, you make beta smaller, and you get something like this. Okay? So Yeah, there is a particular value of A, something like 2 point something, which is the best thing. Because actually you should do this for self-avoiding walks. Yeah, exactly. So there are ways to choose an A to... Yes, exactly. Okay, so here's my last slide. There are interesting other ways of looking at the pinning model. Here's a paper that Francesco was involved in that you try to do a kind of renormalization analysis, sort of looking at bigger and bigger blocks and doing a kind of multi-scale argument. Nicolas has looked at stuff where the interface is more complicated. It has an internal structure and that may affect the behavior significantly. And it's also possible to make the interface, instead of flat, to give it some random structure, and that has been looked at in a couple of papers that are here. So I'm ready to give you my daily take-home message. Random pinning is a simple model, but with a deep behavior. We've been able to get our hands on this deep behavior with a rather fancy large deviation principle that looks at words cut out from a random letter sequence. What came up in those in that analysis was not easy, but it was explicit. It was dealing with relative entropies, and we were therefore able to really still write down some expressions for that, and I think it's sort of even remarkable that you can write down these things, because it's quite rare that you get variational formulas for critical curves. And there was an interesting application to DNA, even though the one had to have quite a leap of faith to apply to that, but that's fun. Thank you very much. Eulalia.
In this corollary 6,
Yeah?